talk about black box testing of automotive systems. In the last few years, many security holes have surfaced for automotive system. And what's surprising about these vulnerabilities is not it's not surprising that there are security holes in connected cars, because connected cars are just like computers. They have infotainment systems, they have a computer on board, an ECU, and that part is not surprising. However, what is surprising is the fact that the systems are very much connected. So this means the vulnerability in the Bluetooth, for example, or the Wi-Fi or the mobile part of the system can lead to compromise of the computer itself. So this could result in loss of guidance or attacks that actually affect the way the car drives. And of course, this is very dangerous and very concerning, because taking over a car remotely is a big deal and is actually life-threatening. So you can see here some examples for vulnerabilities that were found. Some of them are direct vulnerabilities where you need direct access, for example, to the OBD port. Some of them, you don't need to be in the car, but there are physical, so things like CD, vulnerabilities in the CD. So if I have access to the CD somehow, there are some things I can do. And then short range and long range vulnerabilities, which are, of course, the most concerning and the most critical, because short term means that if I'm anywhere near the car, even if I'm outside, there are some things that I can do. And then long term means that I can be anywhere in the world and maybe take over the car systems. And you can see some of the results. So some of them result in complete full control. And this is a big deal. Another thing we've seen are some live demonstrations of these attacks, and that sort of shows us how things can actually work in the real world. This is not just the theoretical issues. Two security researchers by the name of Charlie Miller and Chris Valasek actually did a live demonstration where they remotely took over a Jeep and were able to sort of hijack the controls and shut it down or have it drive into a ditch. So these things are very much critical vulnerabilities in the ECU, in the infotainment, in the other parts of the connected car. As cars become more and more computerized, this threat is actually going to grow. Now, the car manufacturers actually responded pretty quickly to these attacks, and they're worried not just about the vulnerabilities that were discovered. This is, of course, a big deal and very important, but they're more concerned about future vulnerabilities. The reason is, as I mentioned, cars are going to be more and more computerized as time goes by. And then also code changes quite frequently. So there are constant upgrades. And this means vulnerabilities are likely to show up again and again in the future. So as a response to all these issues and future issues that might come, Ford, just as an example, has set up a cybersecurity testing lab. So they have their own team internally doing security testing, and they are testing whatever vendors are offering them. So they're testing ECU, they're testing the different infotainment systems, they're testing various car components on different car versions, and of course different versions of those systems. So vendors can pretty much expect that security testing will be done on their systems if they're involved in any one of those components. So if they're somewhere on the CAN bus, if they have access to the USB, Bluetooth, Wi-Fi, any other connected parts, infotainment, they might be tested. BStorm is one of the tools that is being used in this testing for unknown vulnerabilities. And if there are failures, then these must be corrected. And then a lot of time that's a condition within the contract. So vendors offering components to cars by these manufacturers should expect that security testing will be done on the code, and that if there are any security holes that they might suffer for that. In the GM case, General Motors actually mandated testing by all vendors. So GM has their own cybersecurity unit that does their own testing, but they've also required the vendors themselves to do testing with a testing tool, which is BStorm or an equivalent tool. It is called, the internal number appears here, and then you can see one of the paragraphs is the fact that you must use fuzz testing tools within your development process. So GM can actually have you show proof that you have done fuzz testing on your systems before they will integrate or implement your system. Now, who's being tested is pretty much anyone that will serve any part of the connected car. So anyone on a CAN bus can be expected to be tested. Infotainment will definitely be tested, and anything that has to do with connected cars. So inputs such as USB, Wi-Fi, Bluetooth, different file formats. If you are doing something that has to do with computing, you will probably be tested. Other systems that are actually have been tested, and we saw them testing, could be things like the steering wheel, it's connected to the CAN bus. It could be the gear shift and transmission and other things. In the future, or not really the future, more like the present, even are things like smart chargers and other things that are being added to cars. As this is expanding, more and more things are expected to be included in the testing. Now, this is an example of a test that might be done, and on the different levels that it will be tested. So in this case, we're seeing the stack where we've got IPv4, and above it there's ICMP, and above that there's HTTP and HTTP2. And tests are going to be done in a different layers. So tests are going to be done on every one of those protocols, and they can be done by sending malformed packets. They can be done by resending different things. And to sort of illustrate how the testing is done, I want to explain a little bit more about black box testing and what that is. So the idea behind black box testing in general is the fact that even if we don't have the source code, and even if we don't have a lot of knowledge about the system we're testing, we can still test systems by attacking the inputs and seeing the behavior. So this is where the name black box comes from. We're treating the system as a black box. In this case, if we're talking about an infotainment system, or if we're talking about a component that goes into the car, that component has some kind of input, some kind of computerized input, and then there is either some kind of behavior, something happens, or it generates an output. And by attacking the inputs, basically sending different inputs and watching what comes out, we can discover security vulnerabilities. And it's not as important to us what happens inside, which is, again, why we call it a black box. It could be a black box to us, and we will still find weaknesses. By the way, black box testing is the main way that security testing is done today. So most of the vulnerabilities that I have described, and most of the vulnerabilities that are out there are discovered with black box testing. Now, what is important when we're doing black box testing? Protocol coverage is usually what's important. So I showed you in one of the slides before that we want to test on different layers. So if we're testing something that talks HTTP, we want to test it on the IP level, the TCP level, and then the HTTP level. And for each level that we're testing, we want to cover the protocol as much as possible. So in this case, this is a CAN bus type protocol. And ideally, we want to make sure our testing covers everything, all the different fields. And the advantage we have as the ones doing the test is the fact that protocols tend to be really well documented. So we can actually take the protocol documentation and see what are the different fields and what are the different values, of the different fields. And then we can sort of brute force it. So we can go through the different options and go service ID by service ID. And then if there's sub functions, we'll go through them. And then we'll start inserting invalid data into some of those fields, and again, observe the reaction or the output. But by going through all these different combinations, we can guarantee protocol coverage, which is important for us to say that, yes, we have tested everything, or we're pretty comfortable that our coverage is complete. Now, what are the different test results that you can expect with BStorm? So as I mentioned, the first thing that's important is we try to test all the different inputs. And with connected car, that could be Wi-Fi, Bluetooth, all the various attacks on infotainment systems. We're going to try all of those inputs on all of those different directions. So, and then we'll try all the protocols that are being supported there. Those inputs can sometimes be surprising. One recent example of different inputs that we're testing is USB. So USB is not something that we usually think about when we think about a protocol, but in fact, USB is a protocol. USB is an input. It's a way to connect to the system. And in the case of USB, this is a very low level protocol. It's usually something that is dealt with by the motherboard or the operating system of the device we're using. And this means an attack, a successful attack on the USB subsystem can give us a lot of control over the device and can allow us to do many, many different things. So the USB type attacks are one example, one maybe surprising example for inputs that we'll test. We want to test all other inputs, not necessarily the ones that are wireless. I'll give an example for why USB testing is important, even though a lot of people think, well, if it's USB, I need physical access. The fact is, a lot of components use USB, and a lot of these components might be wireless. So I might have a wireless device connected through USB to the infotainment system, which is connected to the car's computer. And using this chain, sort of control chain, if I can attack the wireless device and take control over that, and then find a USB vulnerability, I can go into the infotainment system. If I'm in the infotainment system, maybe I can find an attack again on the CAN bus or on the car's computer, and then I can take over the chip as you saw before, or do some kind of other attack. And this is why it's important to test all the different components of the system, even the ones that seem not relevant. So I've mentioned the steering, things like steering wheel and transmission. So again, a lot of people think, well, if there's a vulnerability in the transmission, why do we care? Transmission is very internal. Who's going to have access to the transmission system? And again, the answer is many devices can. There's devices that monitor it. Maybe I plugged in something over a CAN bus that also talks to the transmission system. And since these whole things are connected, I can, again, create a chain of attacks that we want to prevent. So the first thing is we will be testing all the different inputs. And when you think about your car, or if you're a vendor producing a component, think about all the inputs your component has. Inputs are network, inputs are hardwares, inputs are file types. One big vulnerability in infotainment systems nowadays that we always test for is attack via file types. So if there is a vulnerability in processing, for example, MP3 or MP4 files, this means I can attack through the podcast system and have a malformed, or the music player, and have a malformed MP3 play on the infotainment system. And again, if that means I can create a chain of attack where remotely I'm triggering a vulnerability on the car itself. So literally all the inputs will have to be tested. What kind of tests do we do? So we do a few different types of tests. Some of them are field level attacks. So we go field by field, and we do it again through the protocol description here. We know what the field is like. So we know if it's an integer, we know if it's a string, we know if it has certain value, and we'll try to do attacks in those fields. One example for attack is an overflow. if I know there's a certain number of characters, if we take again MP3 as an example, if there's a name of a song and the name of a song is usually just a few characters, we'll try to put 1,000 characters in the name of the song and see what happens. If there's a field here that is supposed to be only 1 byte or 2 byte, we'll try to put more bytes into it. We'll try to do integer-based attacks. So if we're expecting a number, we'll put a large number, we'll put a negative number, we'll put 0 as a number, and then anomalies. So anomalies are completely unexpected things. If we get, if we have a function here that has 1, 2, 3, 4, 5, 6, 7 subfunctions, we'll try number 8, an 8 subfunction, which is an anomaly that should not be supported. And again, the purpose is to see how does the device behave and what kind of output comes out from these things. In addition, we do structural attacks. So structural attacks basically means that we try to play one field against another field. There's a structure here. So other than the field by field, there's also a complete structure. And as we look at the structure, we try to see what kind of attacks can we do on the structure. Some simple example would be length. So in many cases, one field represents the length of another field. So we usually have maybe a byte that says, here's the length of the field we're going to give you, and then we're going to give you a field with that length. In this case, we'll put an invalid length. So we're going to tell you that we're going to put 4 bytes, but we'll actually put 5 bytes. Other invalid lengths could be, and it could be +1, -1, it could be a length of 0, it could be a negative length. So structural attacks. We'll try a repetition of elements. So if you're expecting one element, we'll put 2 of them, we'll have them repeat, and then we'll put them out of order. So we'll put elements that should not be. All of these are meant to check either the structure of the request or the structure of the protocol. If there's a back and forth, we'll repeat some requests, we'll put them out of order. We'll again see how the system deals with all these malformed requests. And then the vulnerabilities we're looking for are things like denial of service crashes, memory access. By the way, those 3 things are kind of related, because in many cases, a crash happens because we've accessed a memory location that we were not supposed to. A denial of service also might lead us to part of a code that we were not supposed to reach. And this type of memory access can sometimes lead to code execution and slow response. A slow response is what can help me shut down the computer or have the computer not respond to commands. If the brake system are computerized and I can cause the ECU to not really respond, then that means my brakes might be out of order, for example. And then an example for a report. This is an example from the BStorm black box testing tool. The purpose of the report is to let you know exactly what we found, what kind of attacks we found, and let you reproduce the attack as much as possible. So the dual purpose here is, of course, to uncover attacks or to cover the protocol and say that we believe the protocol is very safe and that there were no attacks that we could find, but also on the attacks that we did find, to help you, the person who developed the system, to reproduce the attack and then to mitigate it. So we start here with some general settings to let you know what we tested, what kind of protocol. Right here, in this case, we tested an OBD2 protocol, all the different settings that were done in the testing. So you can set it, do all the testing on your end and repeat the same exact testing procedure. The exception that we caught. So for every exception that we caught, for every problem that we were able to detect, we'll give you all the information that we found. So we found this exception at this time, and then we know exactly what the attack was. So we can tell you that we tested this specific part of the protocol. So we tested the engine RPM major component, that specific part. And then what did we do? So the test that we did was a repeated FF. We sent FF many times in a repeated way. And then what happened? The device stopped. So we could not get a response. And again, this could indicate that we accessed memory that we were not supposed to access. And then the device crashed. It could indicate denial of service. It could indicate that we were able to execute code in some way. All this can cause the device to stop. So in order to first of all mitigate the issue, you need to look at the part of your code that handles this RPM major component field and see why does the repeated F cause it to crash. Now down here you can see the actual request. So you can see that we sent FE41 0C and then a few Fs, FFFF, and then we continued normally with the protocol. And the report itself will also have a Perl script or Python script, which allows you to actually run the attack again. So we'll give you a proof of concept script that you can use in your lab or in your environment to recreate the attack outside of BStorm. And finally, here is where you see all the tests that were done. So we'll show you the entire protocol, all the fields, everything that was tested, and you can see that we're here in the middle of testing of this field. So this is important because again, we can guarantee code coverage, or we can show that we were attempting to do complete code coverage. And this is important if your car manufacturer is asking you what kind of tests have you done. You can say, well, I tested the OBD2 protocol and I've done all these tests on all these different fields. And finally, the different components that are here, and this sort of maybe we'll tie the whole thing together. The way that BStorm works is we take, again, the protocol description. So we'll take HTTP or CAN bus or OBD2 or Wi-Fi, Bluetooth, anything. We'll take the protocol itself. We'll translate it into an attack language. So that's basically the different fields, which allows BStorm to start generating attacks here. So the attacks are generated sequentially, field by field, generating these attacks, sending them over to the target. We can send it over Wi-Fi, over Bluetooth, over USB. We can send it directly, we can send it over IP, we can send it over CAN bus. We support automotive Ethernet and all the other interfaces. So sending it to the attack, and while we're doing it, there's a monitoring component, which is watching basically the system and monitoring that for exceptions. And as soon as an exception is caught, we will report back to BStorm. BStorm will record the exception, and then we'll know exactly what is the attack vector that will be sent. And this allows us to give you all the information about the attack and have you recreate the attack if you need to. So different components, and this all comes as part of the BStorm system, are the module description itself, which you can edit and change and fix, the generator, which takes the attack and generates sessions from it, and then the monitor that monitors for exceptions, notifies BStorm, and generates the report. This is the end of my explanation on automotive testing and how some of the tier 1 manufacturers are doing security testing and how to do it with a black box testing tool like BStorm. I'll be happy to answer any questions and happy to hear from you. My email here is below, and looking forward to continuing the discussion.